Hello, welcome to this short presentation of COOL-CHIC, a low-complexity learning-based image codec. So COOL-CHIC is an algorithm which compresses images, and its main idea is to learn one decoder for each image to compress. This is quite different from what's usually done in the literature, where people tend to learn one autoencoder on a big training set. At the end of the training, the weights of the autoencoder are frozen and used to compress any possible image. As such, in order to offer great compression performance on a wide variety of images, the autoencoder must have a large number of weights and so an important complexity. This might hinder the adoption of learned codecs. In this paper, we propose to do an opposite approach, where instead of learning one universal decoder, we're going to learn one decoder for each image to compress. As such, the complexity of our decoder will be very reduced, since it will be perfectly adapted to the image to compress. So let's see how our decoder works. Everything starts from the bit stream, where we see different colors for the different quantities which are sent from the encoder to the decoder. In green, blue, and red, we have the parameters of our different neural networks composing our decoder. The first neural network, in green, is an autoregressive probability module, which is used to drive an entropy coding algorithm, which in turn helps to decode the big gray chunk of the bit stream, which represents the latent representation of our image. This latent representation is a hierarchical representation, which is a set of 2D latent grids, and it will go through two steps. The first one is an upsampling step, which is achieved by a very lightweight neural network, and this allows to obtain a dense representation. Then, this dense representation is fed to the synthesis transform, which is our third and last neural network, and this synthesis maps the dense representation to the decoded images. So, as I said before, our goal is to learn one decoder for each image to transmit. So, encoding an image means learning the best parameters, so the best latent representation and the best neural network parameters for each images, and we learn that by optimizing a rate distortion cost, which is the distortion between the compressed and original image plus the rate required to decode this image. Now let's see some results. So on this graph here, you see the complexity of different approaches on the x-axis. So the smaller the complexity, the better. It's the complexity on the decoder side, which is often the most important complexity, since it must run on a variety of low resources devices, such as smartphone or laptop. And on the y-axis, you see the relative rate required to offer the same quality than a conventional codec HEVC. So if you are at minus 10%, it means that you need 10% less rate to achieve the same quality than HEVC. On this graph, we see two kind of systems. In red, we have our proposed system, and in blue, we have two different autoencoder-based systems. So the first thing to note is that our system are significantly less complex than autoencoder-based one, since we require around 1000 multiplication per decoded pixel, while autoencoder required quite often more than 100,000 multiplication per decoded pixels. Then we see that even though our approaches are very low in complexity, they offer great compression performance, since they are either competitive or better than HEVC. Moreover, they can outperform some autoencoder-based approaches, such as the ballet approaches, and they even come close to some high complexity autoencoders, such as the Cheng autoencoder. In the end, this paper presents a low complexity learned image coding, which, unlike previous work, learn one decoder for each image to compress, and this results in a lightweight adapted decoder. Since it is both low complexity and quite performant in a rate distortion sense, This paves the way for learned codec usage on devices with constrained computational resources. Last, everything we've done is available on GitHub, so you can either compress your own images using our model or try to decode some bit streams that we provide, and that allows to replicate the results presented in the paper. Thanks for your attention. Bye.